Welcome everyone to tonight's session on carboxylic acid derivatives. Let's start with the basics. What is a carboxylic acid derivative? Well, first, we have to know what is a carboxylic acid. A carboxylic acid is a functional group on a molecule that has a double bound O, a carbonyl carbon, and on that same carbon, I also have an oxygen and a hydrogen. So it's a hydroxy group and a carbonyl on the same carbon. This is a good acid. You've seen it in resonance. You've seen it in a lot of different chapters, depending on which piece you're studying. But today, we're going to take it to the next level. If I take that OH group away and I put something else in its place, we'll call it Y. This is considered a derivative of carboxylic acid because it was made by swapping the carboxy's hydroxyl group, that OH, for a Y, and that is what we're going to be studying today. Now, it's not just about knowing what the derivatives are or how to form them. Your professor may show you something like this. Let me know in the comments if your professor likes these kinds of questions. Starting with benzene and any other inorganic reagents, somehow, someway, show how you would come up with a product that looks like this. That means you have to know many different reactions to put it together, and you probably do. Maybe you remember that you can do an electrophilic aromatic substitution, that you can put a group on the ring, but maybe that group you're putting on is an acyl group or a carbonyl or even just an alkyl chain that you oxidize to a carboxylic acid. The question then is, how do I get that methyl group on there to turn it into an ester? That is where carboxylic acid derivatives come in. Now, what we're going to do today will be the basics. We'll go through a lot of the different reactions and mechanisms. But for even more practice, to make sure that you really get to apply what you learned today, make sure you sign up to get a copy of the worksheet, which I just finished putting together right before this session, with a lot of different practice questions that you will be able to do, that you should know how to do as soon as we're done with this session. So let's learn about derivatives, starting with the most reactive one, the simplest one, and that is an acid halide. When you hear the word acid halide, what comes to mind? The acid part is telling us that it's a derivative of the carboxylic acid, but instead of the OH, I'm going to put a halide, a halogen. And that halogen, for example, Cl, is called an acid chloride. You'll also see it called an acyl halide because this technically is the acyl group. And so this right here is an acyl chloride, specifically as our example for the acid halide. The next one that you have to know, I'll show you the basic ones and a couple more advanced ones, but I'll focus on the common ones that you have to know. The next one is an acid anhydride. When you see the word anhydride, that's one word, I don't know why it's pretending to look like two. What does the word itself tell you? What does it look like it should be? Anhydride means an, without, hydride, water. An acid anhydride, I want you to imagine as if you have a carboxylic acid and another carboxylic acid, but we take out a water. We took out H2O, and what we're left with, let me show you in two different colors so you can see exactly where this comes from. What we're left with on the left is the carbonyl with an O. The H is missing. On the right, the O and the H both came off, and that is an acid anhydride. It just looks like two carboxylic acids were fused together. The next one that we're going to look at is an ester. An ester is a functional group that you've probably already seen quite a few times. It starts out as the others, looking like a carboxylic acid, but it still has the oxygen, which, well, the anhydride technically also had an oxygen. The difference here is the piece we're adding is a CH3, or in this case would be an R group, for example, a CH3. And the last one that you absolutely have to know is the amide, which also looks very similar to what we have above, except instead of having an oxygen there, we have a nitrogen. And we'll keep this one simple. We'll just put an H2. Now the ester and the amide could both have a chain on it. So here we have a CH3. It could be a longer carbon chain. The amide, let's change this one up a bit. Nitrogen has 2 bonds, so I could make one of them a hydrogen and one of them an R group. And the reason I'm showing it to you this way is you can have another functional group that looks very similar. And that is, if I take a carbonyl here, about to draw an ester with an R group, but I take that R group and I actually attach it. So notice this is the R group that is sitting on the ester, but it's all on the same chain. It's one long molecule. This is a cyclic ester. Can anyone tell me the name of a cyclic ester? And if I do the same thing to the amide, I have my carbonyl, I have a nitrogen, and the R group happens to be attached in a ring to the parent chain. We'll give an extra hydrogen because nitrogen has an extra bond. And this is a cyclic amide. What is the name for both of these? I'm not seeing any answers. If you're not sure, put IDKY in the comments, which stands for I don't know yet. Because you don't know yet, but you're about to learn. This is really important because professors like to test you on them, and they like to trick you on them. That's the important part. If you have a cyclic ester, this one is called a lactone. And the way I remember the lactone is it has that O, that oxygen, lactone, that O, the functional group that has the O. And the cyclic amide, the way I remember this one is a lactam. Lactam has the M for amide. Okay, do not mix up your lactones and your lactams. Make sure you understand the tricks for remembering them. And so here are the 4 main groups again. I'll write it next to each other on this page. If we have a simple carbonyl, and then attached to it, I have the halogen. This was my acid halide. This is the most reactive of the carboxylic acid derivatives. Slightly less reactive is a derivative that has an O and a whole second half of the molecule, the anhydride. Slightly less reactive than this is the derivative that had the OR group, and that was our ester. Now, the ester is about as reactive as a carboxylic acid, but the reason I'm not putting the carboxylic acid in this ranking is because we're talking about the reactivity of a derivative, and this is not a derivative of itself, it's just a carboxylic acid. And then slightly more reactive than that is the amide. That was the derivative that had nitrogen and either hydrogens or R groups or both. I'll keep this one simple with an NH2. So again, the acid halide is most reactive, and I will show you why in just a moment. The amide on the right is least reactive, and this is the order. Now, this is really, really important to know because in addition to knowing how to make all of them, you also want to know how to go between them. So you can learn the individual reactions, but I challenge you that when you look at them together, you'll realize, wow, this is actually not as hard as they're making it seem. This one can turn into anything. because it's all the way on the left. The more right you go can only be turned into whatever's there on the right. But the ester can be turned into a carboxylic acid simply with an acid catalyst and water. The amide can also be turned into a carboxylic acid by reacting it with acid and water. So I'll just put H3O plus for an aqueous acid. And here's the important one. You can turn a carboxylic acid into an acid halide, as we'll see shortly, using SOCl2. And that means any derivative that you want to create, just start with something least reactive and go towards more reactive. But if you need to go backwards, turn the amide into a carboxylic acid, turn the carboxylic acid into an acid halide, turn the acid halide into anything else. If you want to see how to do all these reactions, give me a couple of hearts. And let's take a look at how it goes. So let's start with the basic mechanism. So the basic mechanism for any of the carboxylic acid derivatives should look very similar to a reaction to many types of reactions that you have already seen. I will put Lg here for leaving group. That leaving group could be whatever you have as the derivative. And actually, before I go into the mechanism, let's move this down and let's talk about the carboxylic acid concept itself. A carboxylic acid is acidic because of that hydrogen. And so as long as the acidic hydrogen is there, it's hard to attack anything else because that hydrogen is vying for attention. But if I deprotonate the carboxylic acid, I get a carboxylate, which has a negative charge on the oxygen that I just deprotonated. But this negative charge can resonate. And when it resonates, I get the reverse. So now I get a single bound at the top. Let's show these electrons in purple. Whoops. Okay, so we have the green oxygen, the 2 lone pairs that were already there, and the purple electrons that we just added negative charge came up. We have the electrons that we'll show here in blue, and that means the oxygen on the right only has 2 pairs. The blue electrons are sitting as a pi bond, and all we did was shift where everything is. This is relatively stable. We want to keep this in mind. But if we are looking at a leaving group that does not have that hydrogen, then the resonance itself still exists. Remember that the oxygen with a pi bond can resonate up, giving me, when I look at the neutral structure, I really have a partially positive, a partially negative oxygen, a partially positive carbon, and that is key. This means that if I have a nucleophile, remember, nucleophile, nucleus loving, the nucleus is positive, the nucleophile is negative or partially negative. It's got electrons that want to attack something positive, and that nucleophile is going to attack at the carbonyl carbon, kicking up the pi bond that's already kind of resonating up and down, so it doesn't mind getting kicked up. This is where it gets interesting, because if you think about your carbonyl reactions, for example, when you had your ketones, your aldehydes, once the carbonyl got kicked up, you were left with, let's show these electrons in purple, you were left with a negative charge there that was waiting and waiting, and then you had to protonate it or you had to do something else to it. But now, if we have a leaving group, then the electrons can come back down and kick out the leaving group. If you kick out the leaving group, what you did here is reformed, well, we forgot the nucleophile. The nucleophile is still attached. Right there. We reformed the carbonyl, and that means we have the 2 lone pairs. Those are happy. The purple electrons are now sitting here as a pi bond. This is a stable molecule. It's happy. And then I have a leaving group off somewhere in solution. And this, understanding what happened here, is going to explain what is going on in this chart. Think about any reaction. What drives a reaction? What makes a reaction more or less likely to happen? Very simple. You should recognize this from all the other times I mentioned it. When something is happy, it is stable. And if it is stable, it is going to be unreactive. On the flip side, if something is unhappy, it is unstable and it will be very reactive. In the case of a leaving group, if you kick something out and that thing is capable of stabilizing whatever charge just happened, it's capable of handling itself on its own out in solution, it is more likely to stay out in solution. But if you kick it out and it's very unstable, it is going to come right back, or it's never going to leave in the first place. And so when you're looking at a table like this, what you want to pay attention to is what happens to the leaving group. What is it that I'm kicking out, and how is it going to behave in solution? I don't know why that just happened. Let's put it on the bottom. So let's take a look at why the ranking is this way. Because your professors will test you on it, I don't want you to memorize it. I want you to understand what happened. The acid halide kicks out a halogen, in this case a Cl-. If you remember from way, way back when you covered your acids and bases, are halogens happy and stable to hold a negative charge, or are they considered reactive and wanting to attack everything? Halogens are very stable. They're, except for fluorine, which we're not going to look at today because it's too small, but they're larger, they distribute the charge all around themselves, they're not too reactive, they're really, really happy in solution, they don't mind. They're so easily kicked out, that's what makes the chlorine or the halogen the most reactive of the derivatives. The next one we have is the anhydride, and what we're kicking out is a molecule that has a negative charge on an oxygen, which is capable, right? Oxygen is electronegative, but not only is oxygen electronegative, the oxygen can resonate, and so we really have two rather than one oxygen atoms holding that negative charge. And if we have two atoms holding the charge, it's more stable, it's more distributed. Of course, it's capable of handling itself in solution, and that makes it very reactive. So reactive that when we were doing this in lab, somebody in the lab didn't realize that you don't put this thing in water. He put a tiny flask with a tiny amount. I think he was washing the dish that he had the anhydride in, and the whole thing just started steaming and smoking and bubbling. It looked like something was going to explode. Don't ever put this underwater because it is very, very reactive. The next one we have is the ester. And what we're kicking out here is an OR minus. In this case, we have an OCH3 minus, which is just an oxygen atom holding the negative charge. It's not unstable per se. We already said that oxygen is pretty good at holding that negative charge, but there's nothing to balance, nothing to stabilize. It's not ideal, and so the ester is not as reactive of a derivative. And last but not least, the amide. What we're kicking out is a nitrogen. Nitrogen, in this case, would be an NH2 minus. If you remember from your early reactions, NH2 minus amide is a very strong base. One of the only bases that will deprotonate a terminal alkyne even when an OR will not. That is a very, very, very bad leaving group. So let me know in the comments, even if you're watching the recording, comment below. Do you understand why this is most reactive, best leaving group, and this is least reactive, worst leaving group? Meaning, do you understand logically the reasoning behind the stability chart here? For students who joined late, yes, if you go to this link on my website, you will get access to a link to the recording, the notes that I'm writing in today's session, and a worksheet that I wrote with quite a few practice problems on everything I'm covering today, so that you can take what you learned and apply it to even more practice and make sure that you understand what you're covering. All right, so now that we understand the stability, let's go into the specific mechanisms. Now, we're not going to have time for all of them, but I'm going to pick a couple of the key ones that you have to know. Starting with, I told you when we looked at the chart that the best way to do a reaction, if you don't remember how, is to just turn your carboxylic acid into an acid halide. Now, here is a trick to help you with the mechanisms. I want you to think of this question. What's the nucleophile? What's the electrophile? Or what's the most positive? Yeah, let's ask it this way. What's the most negative? What's the most positive? And then how does the attack happen? This will help you figure out, so what's my next step? What's my next step? Because you have so many steps at this level that it's very easy to forget unless you have a pattern to follow. So we have our carboxylic acid derivative, and we're reacting it with SOCl2. So this is an overview of the reaction. We have SOCl2 in pyridine. Do you remember when you did substitution reactions and we had an alcohol as a really bad leaving group? We said, what do we do with a bad leaving group? We bribe it with SOCl2 and turn it into a halogen. It's the same exact reaction. We have a bad leaving group, we bribe it and turn it into a halogen. So let's see how that actually happens, keeping in mind the question, what's the most negative? What's the most positive? What's my attack going to look like as a result? I'll start with a very simple carboxylic acid and show SOCl2 as follows. S double bound O with 2 chlorines. Remember that just like a carbonyl can do resonance, so can the sulfonyl, sulfur bound to oxygen. And that is important because the very first step is going to be an activation of the carbonyl carbon, which is going to attack sulfur and break the bond between itself and oxygen. This is where things start to get a little bit messy. So I want you to pay very close attention to the colors that I'm using, because if you can follow the electrons, colors, bonds, atoms, you'll see exactly where it came from. The reason I do everything in color, just as a heads up, I have ADHD and I would have a really, really hard time following this. And if I'm the one teaching it and I have a hard time, I'm not going to expect you to follow it all in black and white. So let's do it all with colors so we can carefully see where everything is going. I have my carbonyl, I have my red electrons. My blue electrons are now sitting as a bond between oxygen and sulfur. Sulfur now has just one oxygen attached, as one bond to oxygen. I'm sorry, we'll put these electrons in orange like that. And then we have our 2 chlorine atoms, 1 and 2. It doesn't matter if I have them on the right or the left because this is a 3D molecule that I'm showing in 2 dimensions. Another thing you want to look out for are making sure that your charges are always the same. The net charge in every step. And so this starts out neutral, no charge on either molecule. The most negative is an oxygen with all the electron density around it. The most positive is the sulfonyl because of resonance. And as a result, the oxygen here now has 3 bonds, 1 lone pair, and a positive charge. And the oxygen here has 3 lone pairs, 1 bond, and a negative charge. Just like with the carbonyl that I showed you before, even though the oxygen is stable enough to hold that negative charge, that sulfur is still partially positive. Chlorine is a good leaving group, and so oxygen is going to take advantage, collapse the electrons back down, and kick out one of the chlorine atoms. That is key because we're going to use that chlorine in a moment. So what do we have? We still have this right here. Oxygen here is still double bound. We have This bond here to sulfur, which is now double bound to oxygen, only has one chlorine. There's another chlorine off in solution we'll get to in a moment. This right here is still positive. This all is neutral. So where did that negative charge go? That negative charge is now the chlorine, or rather the chloride, because it has that extra set of electrons. We'll show these in blue, sitting right here. And the electrons that collapse down, these are sitting right here. So let me know in the comments if you follow. I know there are a lot of steps going on here. All right, so we have chlorine kicked out of the SOCl2 molecule, but nothing yet happening to the carboxylic acid. So we need to make things start to happen. That's where pyridine comes in. This is an acidic hydrogen. And so different professors will show it in a different step, but this is about where it happens. Pyridine will come, grab that hydrogen, and give this oxygen back its electrons. But it's not just going to put the electrons here. This oxygen is positive. There's still resonance going on. And so the electrons will actually just go in this direction to form a pi bond between carbon and oxygen. If we form that pi bond, there will be too many bonds on carbon. And so we're going to, let's make these electrons pink. We're going to kick these electrons up. So notice it grabbed and just collapsed the electrons upward. What does that leave us with? We still have the oxygen attached here. One bond to the upper oxygen. That upper oxygen had a red lone pair. Now it gets a pink lone pair. It's only got one bond. This oxygen here had the blue bond. It has two purple pairs of electrons, but now the red electrons that used to bind it to the hydrogen are sitting like this as a pi bond. And of course, we still have the S double bound to an oxygen and a chlorine. Okay, so nothing much going on. Somewhere in solution, we have our pyridine with an H. It's got a positive charge. This is going to balance the solution, make sure that we don't form HCl, hydrochloric acid, because that would be too strong. But we're still not anywhere near our derivative, so what happens next? Remember that chlorine we kicked out? Are we missing a charge? We had a net positive. The net positive is right here. No, we are good to go. This is where the excitement happens. Let's bring that chlorine back. We'll show the chlorine with all the lone pairs and a negative charge. Chlorine, remember, is not very reactive, but in this case, this is so partially positive, it's so attackable that chlorine can't help itself. It wants to attack. It's attracted to that partially positive carbonyl carbon. And this is where it gets a little bit messy. Chlorine attacks the carbonyl carbon and kicks the electrons up onto oxygen. Now, some professors will show this all in one step, so I will draw it, undo it, and show it to you in two steps, just in case you're not following or it's too many arrows. But as soon as the electrons collapse onto oxygen, they are going to go back down, and that gets kicked out. Let me show it to you in two steps so that you can see exactly what is going on. And here we go. All right, so we have this right here, oxygen, another oxygen, and now here we have a chlorine. The oxygen at the top has one lone pair, two lone pairs, a bond to sulfonyl chloride. The oxygen on the bottom has the two purple lone pairs, and it just got a third lone pair because of the negative oxygen right there. And what did we say happens? It collapses back down. So these electrons will come right back down. Oxygen was a bad leaving group, but now the fact that it's attached to all of that, it became a very good leaving group. And so what color will make these electrons purple? This entire thing gets kicked out to form a bond here. Let's see what that looks like. We have a carbon chain, which we kept small. We have one bond to oxygen, one bond to chlorine, which has another 3 lone pairs. The oxygen that was attached is sitting here with, it's got the purple lone pair that just came from getting kicked out. Actually, no, that purple lone pair is sitting as a bond. Disregard. We have the pink lone pair, the red lone pair. It had a light blue bond to sulfur. And then it has that purple bond that came from here. So that's it on the side. And then what happened to the bottom oxygen? It had the 2 purple lone pairs, and the red lone pair is now sitting as a pi bond. So this molecule looks a little bit upside down and drunk. Let's just do a redraw. I'm just going to flip it around so that I have my carbonyl facing up, the pi bond in red, the lone pairs in purple, the bond to chlorine, keeping everything the same, just making it look a little bit less drunk. And look at that, my acid halide. My acid chloride, and then somewhere off in solution, I'm going to redraw this, just looking a little bit less in nuts, is a sulfur, double bound oxygen, single bound chlorine, double bound oxygen, a very, very good leaving group, which is why this whole thing was able to happen. That was a lot. A lot. So let me know if, I'm not looking for you to necessarily have the whole thing down, but do you feel like if you watch this 2 or 3 more times or just study the notes a few times, do you feel like you got this reaction? Simply, I don't understand your question. So let me know if you followed along, and I hope you see why we're not going to go through every single reaction. But this one is A, a difficult one, and B, something a lot of professors do test. And so I want to make sure that you have the ability to study it, to see it, and to be able to do it on your own. Excellent. So let's say you don't have to do the entire reaction. Say you're just given a molecule that looks like this. It's got a carboxylic acid, and you're told to turn it into an acid halide. Very simple. You react it with SOCl2, put it into a solution of pyridine, and the shortcut, if all you have to do is create the derivative, is this. You cross out the carbonyl, you draw the rest of your skeleton exactly as you see it, and then where the carbonyl was, the Cl is, and that's it. I'm going to say much simpler, much easier, quite a simple reaction actually, if you don't have to do the mechanism. All right, so that covers the acid halide. The different halogens will have a different molecule that you can use. And the next one, yes, I'm going to show you quite a few reagents and shortcuts because the mechanisms are important, but the non-mechanisms are also important if all you have to do is show the product. So let's take a look. For the acid anhydride, it's another complex mechanism. So I'm not going to go through it in as much detail. I'm not going to go through the mechanism in detail, but I will show you how to recognize and work through the reaction because I want to make sure that you know how to do it. I already showed you that the concept of the anhydride is 2 carboxylic acids fused together. And if you remember that anhydride means without water, anhydride, all we have to do is take out an H2O. Find your H2O minus H2O. This is a dehydration synthesis. All you have to do then is redraw the pieces. What are my pieces? This one right here has an O. This one right here has nothing, just a bond going to nowhere. Bring them together, and that's it. That is your acid anhydride. So if you ever have to create an acid anhydride, you just add a little bit of heat, and this will happen just like that. So that's all you do. Cross out the water, bring them together, boom, you have the anhydride. If you want to reverse the anhydride, oh, I didn't show you the acid halide, how to reverse it. So let me show you that really quick. The mechanism for an acid halide going to something else is so easy. So remember what I showed you. Hold on, let me see where I showed that to you. Here, I told you that the halide is the easiest to turn into anything else. All you have to do is find this thing in red and use that to attack your acid halide. So if I want to go back from the acid halide to a carboxylic acid, all I have to do is react it with what I want. In that case of a carboxylic acid, I just need to react it with the OH is what I want to add, but I need to add another hydrogen. So that's just water and acid. Water as a solvent should technically go on the bottom. Acid is my catalyst. And I could do this in acid or I could do this in base. So I can even do something like NaOH. OH minus will come in. Look how much easier the mechanism is going forward. The OH minus attacks, carbonyl gets kicked up. The carbonyl comes back down, kicks out the chlorine, and boom. I mean, compared to that other mechanism, this is a piece of cake. There we go. Carboxylic. Well, technically, this reaction is not done. What is wrong with the product that I just showed you? Think about what you have here. Think about what I formed. I used a base to create a carboxylic acid. And even though technically this is going to form, the fact is I have so many base molecules in solution, or ions, one of them will immediately deprotonate the carboxylic acid because you cannot, absolutely cannot form an acid in a strongly basic solution. And so that is going to give me, remember how I said this was a very easy reaction? It's still easy, but a little bit more involved than we expected. Because now that I have a carboxylate, all I have to do is throw in some acid catalyst and water. This will get protonated, and then I get my carboxylic acid, which, let's agree, is simple enough, right? Thank you, Omar. I really appreciate it. Question, what's the percent conversion when reacting with SOCl2? I have no idea. If your professor is asking those kind of questions, I recommend asking which resource your professor wants you to follow and memorize those numbers, but I have no idea. All right, so looking at this reaction, let's take a look then at the other shortcut I mentioned. If I want to create an acid anhydride, and I don't remember the anhydride mechanism because, well, Leia decided not to show it on the workshop, and I only learned what was in the workshop. I have a carboxylic acid. I need to turn it into an anhydride. I don't remember how. Here's the thing. Many professors just want the right answer, and there's more than one way to get the right answer. So how about this for getting an anhydride? Turn it into a chlorine. And then what's the other piece that we want to add to the anhydride? How about a carboxylic acid derivative? What am I doing? That's backwards. There we go. How about I react it with a carboxylate? The carboxylate is going to attack, and boom, I found myself an extra step to the right answer, even though your professor was not expecting it. I cannot tell you how many students I've shown this to who have gotten full credit, and the professor said, wow, not what I was expecting, but it's completely correct. That is your option right there. And then the other one I wanted to show you with the anhydride is if you want to undo the anhydride to form your carboxylic acid, then here is another shortcut I want you to recognize. In order to create the anhydride, I told you we take out water. What do you think we should add in if we want to break the anhydride? Well, how about we add in some water, and let's do it in an acid catalyst Don't do this out of the hood because I already told you what happened in my lab when somebody did it. Do this under a hood very carefully. But when you add in water, you're going to get a very violent reaction that looks like this. Here's the trick. You take your molecule, it doesn't matter right or left, and you just slice it between the oxygen. Let me draw this a little different so it'll be easier to see. Just slice it between the carbon and oxygen. Give one side a hydrogen, give the other side an OH. This is hydrolysis. Think of what the word is telling you. Hydrolysis. Using water to break, and look at the pieces. On the left, we had an O, we added an H. On the right, we added an H and an O, and we had this right here, and boom, I got both of my carboxylic acids from the anhydride. Any questions on this? If you don't have questions, put in the comments NQ for no questions, which tells me that you're with me, that you're following, and that you're ready to continue. Aaliyah, I'm not sure what you're asking, so I don't know. The next one, and this is also going to be tested very commonly, is the ester. If I want to form an ester, one way is to take an acid halide, which I've already shown you, react it with whatever is going to be on the ester. We can do it in basic form because there's no carboxylic acid forming. So for example, NaOCH3. What that'll do is, the Na plus is a positive spectator, get rid of it. The CH3O- is going to attack, kick the pi bond up. When it comes back down and kicks out the chlorine, very, very quick and simple reaction, I'm left with an ester. This right here, easy peasy, you are good to go. If you want to show the ester from the carboxylic acid, that's where you get a very commonly tested reaction, and that is Fischer esterification. MCAT students, they love to test this. You have to know this reaction. Fischer esterification is, I'm trying to think if we have time. Let's do it very, very quickly because we don't actually have time for the mechanism, but let's go for it anyway because it's so important that I think it's worth taking the time to do it. We have a carboxylic acid. Remember that it is partially positive over here. And remember the question, what is the most positive? What is the most negative? And then how do they attack each other? We're going to do Fischer esterification by reacting it with an acid catalyst and an alcohol. This is a reversible reaction. You just change the solvent to reverse it. Put water and it'll go backwards. What is the most negative? The carbonyl's oxygen. What is the most positive? The acid catalyst. So that gives me an activated carbonyl. I hope you're noticing a pattern. When we have an acidic solution, well, even without an acidic solution, we typically start by activating the acid catalyst, by activating the carbonyl with the acid catalyst, and that gives me a carbonyl with a positive charge. What is the most negative? My CH3O- in solution. What is the most positive? It looks like the oxygen, but it's not. Let me know if this is something you've wondered before. Why is it that if oxygen is positive, we do not attack the oxygen? The oxygen is a very electronegative atom, and even when it has a positive charge, it starts pulling on the charge from everything around it, making all the atoms around it a lot more positive. This oxygen doesn't see a positive oxygen, it sees a carbonyl carbon that's very positive because oxygen is stealing its electron density. And so this oxygen, we'll show the electrons in blue. this oxygen is going to attack the carbonyl carbon, kicking these electrons up to give me my activated intermediate that looks like this. I have my green OH untouched. I now have the blue electrons sitting as a bond right here to the OH-CH3. And then up here I have oxygen, one lone pair. The orange electrons give me a second lone pair, and I still have the hydrogen from the activation step right there. So now I have an OH here. I have an OH here, and here I have the CH3OH that attacked. It has only one lone pair and a positive charge. The next step, some professors will show an internal proton transfer. Other professors will show it as the solvent grabs the hydrogen and then oxygen grabs the hydrogen from the solvent. The net is the same. And so for the sake of simplicity, I'm just going to show an internal proton transfer where the green oxygen steals one from the purple oxygen. Remember, this is a reversible reaction. If I forget to reverse my arrows, just know that it goes both ways. And that means in the next step, the intermediate looks like this. Oxygen, you know what? I don't want to redraw everything, so let's just, whoops, let's try that again. Let's see what changed. Well, the only thing that changed here is what I have going on with my oxygens, and that is as follows. The green oxygen now has a red bond to a purple hydrogen, and this one right here will show the gray lone pairs like that, and now this oxygen has a positive charge. That is now a very good leaving group. And what do good leaving groups do? Well, they leave. But it can't just leave by itself. Something has to kick it out. And what kicks it out is oxygen from the OH, the OCH3. Either one can do it. Collapsing down to create a carbonyl, kicking the water out because water is a good leaving group. What that gives me as a result, and this time I will redraw it, we have our green oxygen now with a second bond from these orange electrons. It still has the hydrogen, and so now it has a positive charge. On the bottom, we have the OCH3, which kind of already looks like my ester, except I have that extra hydrogen. And so in the last step, all I have to do is a deprotonation. I bring in another CH3OH from solution because I have plenty. It uses one of its lone electron pairs to grab the hydrogen, collapsing these electrons back onto the oxygen, which already has one lone pair. And that is how I get my final product, which looks like this. Green oxygen with that second bond, green lone pair. Now it gets a red lone pair. We had that blue bond from that other lone pair of electrons and OCH3. And that is Fischer esterification. Notice that in this step, I kicked out the water molecule. But if I reverse the reaction and I had an OHCH3 as a good leaving group, that can also get kicked out. What drives the difference is simply the solvent. So the actual reaction would look like this. If I have a carboxylic acid and I react it in the presence of acid and alcohol, then I get an ester, which would be an OR. But if I react it in the presence of acid and water, then I get the carboxylic acid. So these are about equally reactive, which is why here I showed you just an up arrow with an H+, because their reactivity in terms of where they stand in this chart is about the same. Knowing this, here is what you want to recognize. If you have a carboxylic acid and you are told to react it with an alcohol, whatever alcohol they happen to give you. All you have to do is that. Let me show you what that actually looks like. Remember, dehydration synthesis, take out H2O, but technically it's going to be the alcohol, the oxygen from the carboxylic acid. If you look at the mechanism, you'll see it's this one losing the OH. And then redraw it exactly as you see it. So this right here, minus H2O. What we're left with is the carbonyl from the carboxylic acid, the O from the alcohol, and then everything else on it. That is Fischer esterification. And if you have to do an ester hydrolysis, if you're given an ester, no matter how complicated or busy or wacky it is, here, let's do this crazy molecule. The same trick that I showed you before applies. Cut it between the carbonyl and the oxygen. The carbonyl side gets an OH. The oxygen side gets an H. And your product, in the presence of an acid catalyst and water, is going to be the same skeleton that you started with. Carbonyl got an OH. The skeleton here got an H. And boom, I have my carboxylic acid and my alcohol. What do you think of this shortcut? Did you just save, 2 minutes on your exam? I'll say 2 minutes is pretty good, right? Sunlish, you have a lot of broken up questions. So I'm going to ask you to rewrite a full coherent sentence, and let's see if I can answer your question. And for anyone else with questions, go ahead and type it in while I jump on over to the next derivative, and that is the amide. The amide, as you remember, has the nitrogen. And so if I have a carboxylic acid, because the amide is more reactive than the carboxylic acid, I can just react the two directly. I don't need the acid halide, although that would definitely work. So all I do here is I react the carboxylic acid with whatever group I want to add. So for example, if I react it with NH3, then my product is going to be an amide that looks like this. But what if I want carbons on my nitrogen? What if I want something a little bit more complex? Say I have a carboxylic acid, and this time I react it with an amine. That's a nitrogen with an R group on it. What I get here is the same setup for my product, but I have the R group there. So here's what I want you to recognize. However many hydrogens I have on my nitrogen, I take that nitrogen and I replace the OH, but I take off one of the hydrogens. Notice that NH3 went to NH2. All I did is remove one H from nitrogen. Look at that. NH2 went to just NH. And again, the reason is this is dehydration synthesis. So if I draw this out to show you, I have hydrogen on nitrogen. Take out an H2O. Look at that. H2O. Take out an H2O. And that is how you will figure out whatever amine or nitrogen you're given, how to come up with the correct amide. Let's try one more. If I have a carboxylic acid and I react it with a secondary amine. So let's say I have a nitrogen with an ethyl group, an isopropyl group, and a hydrogen. My product, take off one H so that I could take off H2O, is going to be my carbon skeleton, the nitrogen minus the hydrogen, and then everything that was already on the nitrogen. So that is a secondary amide. When I showed you the reactivity, I told you that if you're starting with an amide, the least reactive, we want to turn it into a carboxylic acid and then an acid halide. The nitrogen, the reason this is such a bad leaving group and so unreactive as it is because N as a negative, not very stable. But if I take the amide and I flood it with acid, so let's go back to a simple one. If I take something like this, NH2, and I react it with a lot of acid in the presence of water, let's first show what happens with the acid. Now I have a protonated amide, NH3+, and if I manage to kick this out, so if I bring in a nucleophile, like water, to kick it out, up, down, out, now I'm left with NH3 without a charge. NH3 is stable because it's neutral, and that is how we protonated. Everyone, have you guys heard the expression, we're all equal in death and taxes? So that's kind of how I think of it. Acid is like taxes. It equalizes everything. If something's a bad leaving group, you acidify the crap out of it and you are good to go. And that means once I have, and this specifically would be in the presence of H2O, so it would form a carboxylic acid. And once I have a carboxylic acid, I've already learned how to do all the other reactions with it. Question. In the case of a third N, you mean a third R group on the N, it's not possible? That is correct. If this right here was an R group, I have no hydrogen that I can deprotonate, and therefore I have nothing to take off to do the reaction. So this is where it would stop. You don't do it with a tertiary. You are so very welcome. I wish you the absolute best of luck on your boards. All right, so let's then jump on over and see how this may show up on an exam. Let me know in the comments if your professor is not going to test you on the easy questions I showed you. Let me know if you're more likely to see something like this on your exam. Somehow, some way, using whatever you learned, show how you would form this molecule from what you're given. You know what? Why are we making it so pretty? Let's make it harder. Boom. There you go. Now let's make it a little harder. I feel like branches make everything scarier. If you're looking at something like this and you're not sure where to start, first, if you want to have additional practice, make sure you go to layerforsci.com/orgolive because that's how you'll get a link to the recording, session notes, and the additional practice worksheet questions so that you can try applying what we did today on quite a few additional problems that I wrote up for you. If you have something like this on your exam, as I teach in my synthesis session, the two questions you want to ask are question number one, what's the same? And question number two, what is different? What is the same is my starting molecule, specifically just the parent chain, has 3 carbons, and that parent chain right here is the only thing I recognize. Everything else is different. So I'm asking myself, how can I turn a 3-carbon molecule into that ester? Well, I know that an ester is a carboxylic acid derivative, so I don't yet know the whole reaction, but I do know that I could make that ester from a carboxylic acid. So if I can somehow get a carboxylic acid that looks like this, then I can add this entire group exactly as I see it as an alcohol with an acid catalyst. So then I need to come up with a carboxylic acid. Now, I don't know how to go from an alkene to a carboxylic acid, but I do know how to make a carboxylic acid from an alcohol. If I have an alcohol, I can oxidize it. And that means I need to somehow turn this into an alcohol because this right here, if I can have an OH I can oxidize it with something like Na2, Cr2O7. Okay, so how do I turn this into an alcohol? Hopefully you remember your Orgo-1 reaction. To get an alcohol on a primary carbon, what do I use to get an anti-Markovnikov alkene addition reaction? Hydroboration. If I react this with BH3 in THF as step 1, step 2, NaOH, H2O2, that'll give me the anti-Markovnikov terminal less substituted alcohol, which I then oxidize to a carboxylic acid, apply what we learned today in the Fischer esterification mechanism that I showed you, and that is our final product. Now, if you have a few minutes to practice and think on this, do you think you can come up with the steps for this? Do you think you'll be able to recreate this on your own? No, not game over. Just go through exactly what we did today, and you have this, Selenice. You totally have this. Just give yourself a chance. Now, this is one synthesis question. There's quite a few more on the practice worksheet. Go right here, leahforsci.com/orgolive, and you will get all the additional questions that I wrote up for you so that you get to practice. Now, this is just the topic of carboxylic acid derivatives. Before we talk about the rest of organic chemistry, how do you feel about the logic behind carboxylic acid derivatives? Meaning, I'm not expecting you to be able to answer all the questions right away. Hopefully, when you take a few minutes, you go through the notes, you review the reactions, you practice the mechanisms. Hopefully, at that point, you will feel pretty solid and you will understand what is going on here. But it's just one topic in organic chemistry. What if you could learn and understand every orgo topic in this manner? With beginner sessions like this, where we break everything down so you can learn, followed by advanced sessions to really hone in on the difficult, the tricky, the logic you have to look for when it's not as obvious. If I taught you every orgo topic, Orgo 1 and Orgo 2 in this format, beginner to advanced, do you think that you would have a better chance at finishing the semester strong? Or if you're preparing for an exam and understanding what you need for your MCAT, PCAT, DAT, or whatever exam you're taking? If yes, then what if, in addition to that, you could also ask questions daily? Because if you get stuck with something that you're practicing, your quiz, your exam, you're feeling overwhelmed, well, all of that is covered in my study hall program, and I would love to have you join me. You can find all the study hall details on my website right here at leahforsci.com/join. This is the program that I created for students like myself. The first time I took organic chemistry, I had to withdraw because I was failing the class. I was struggling. I didn't understand. I had no idea what was going on. And I had a choice between an F and a W. I chose the W. The program that I created is basically, I asked myself, what is it that would have helped me succeed? What would I have needed to make sure that I didn't have to go through what I did, so that other students don't have to go through what I did? And that's what this program is. Every concept broken down from the beginning with logic, understanding, foundation, and then building up slowly from beginner to advanced, and the ability to ask daily questions, because I personally have a lot of trouble moving on if I'm stuck, and I don't want that for you. So I'm looking forward to working with you in the study hall at leahforsci.com/join. Again, leahforsci.com/join. I'm going to stick around for a couple more minutes to answer questions in the chat after I log off. And with that, everyone have a wonderful evening. Just keep typing your questions. I think YouTube's going to cut me off in about 2 minutes.